Welcome to 11.2 Permutations. All right, so we're going to start with some dad jokes because who doesn't love a good dad joke? So your dad loves a good dad joke. So here are 6 of his favorites. Want to hear a joke about paper? Never mind, it's terrible. What do you call cheese that isn't yours? Nacho cheese. Why do you never see elephants hiding in trees? Because they're so good at it. Why did the scarecrow win an award? Because he was outstanding in his field. Why don't skeletons ever go trick-or-treating? Because they have nobody to go with. Nobody to go with. What is Beethoven's favorite fruit? Banana. Anyways, thought those were kind of funny. So let's go ahead and use the fundamental counting principle, what we talked about in the last video, to determine the number of ways these jokes can be delivered. So you can choose any one of the 6 jokes as the first one told. Once this joke is delivered, you have 5 jokes to choose from for the second one told. Continuing this manner, it can be shown like this. So for instance, the first joke, I've got 6 to choose from. Then I have 5 to choose from for the second, and then 4, and then 3, and then 2, and finally the last slot I only have 1 joke remaining. So how can we go ahead and use the counting principle? Well, remember we would just multiply these cases together, and so the number of different ways to deliver the dad jokes is simply 720. 6 times 5 times 4 times 3 times 2 times 1. This is actually known as a special number, and we'll bring those into play shortly. I'll tell you what that is all about. Okay? So let's go ahead and look at a possible arrangement, right? So one possible arrangement, maybe he chooses the elephant joke, then Beethoven, scarecrow, skeleton, paper, and then cheese. So that's just one possible arrangement. Now, a permutation is an ordered arrangement of items that occurs when, and this is key, no item is used more than once, okay? So order matters. So the order of arrangements makes a difference. That is key. That's very important, okay? So order makes a difference. Order matters. In order in which these jokes are told makes a difference in terms of how they are received, okay? So let's look at this first example here. How many ways can the 6 dad jokes be delivered if a food joke is told first? So if we take a look, the food joke, how many food jokes do we have to choose from? Well, we only have 2 food jokes. We've got the cheese and we've got the Beethoven's fruit, right? The banana joke. So I would put a 2 in my first slot because I only have 2 choices. The rest doesn't matter then. I could choose any joke I want that's remaining for my 2nd, 3rd, 4th, 5th, and 6th jokes. So how many jokes do I have to choose from for my 2nd slot? Now I'm down to 5, okay? And then my next slot, I'm down to 4. And then my next slot, I'm down to 3, then 2, then 1. So the total here is going to be 240 ways using that counting principle and then multiplying all those together, okay? So 240 ways, and this is when a food joke has to be told first. Okay, I want you to try the next checkpoint on your own. Read through it, come back, let's check our answers. Okay, so I got 120 different ways. In how many ways can you arrange 5 books along a shelf, assuming that the order makes a difference? So the first book has 5 books to choose from. My next book has only 4 books to choose from. Then 3, then 2, then 1. Multiplying all those together, we get 120 different ways to order the books. Okay, here's a little fun fact. If you were to arrange 16 books, different books, for example, the 7 Harry Potter books and the 9 Game of Thrones books on a shelf, and it took you 1 minute for each permutation, the entire task would take you 39,807,439 years. Crazy stuff. Now we're going to talk about factorials and evaluating factorial expressions. So this might be a little new to you. So the product in checkpoint 2 is given a special name. That's what you did. You did 5 times 4 times 3 times 2 times 1. This is actually called a factorial. So I could say this is the same as saying 5 factorial. That's our symbol for factorial. Okay? So a factorial is the following. If n is a positive integer, so we could say 5, then n factorial, that's the way we read it, n factorial, is the product of all positive integers from n down through 1. So if I'm talking about 5 factorial, I would rewrite it as 5 times 4 times 3 times 2 times 1. Okay? So that's what 5 factorial is. N factorial just looks like this. One thing is 0 factorial is actually 1. It is not 0. So let's take a look at this first example. Okay, so let's evaluate 9 factorial over 6 factorial. So how do we write 9 factorial? Well, 9 factorial is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. So what we should notice here is that everything here will cancel, right? So what we really could just do is we could go ahead and say, all right, instead of 9 factorial over 6 factorial, I can rewrite 9 times 8 times 7, and then we have 6 factorial left over, right? So what's going to happen is those 6 factorials will cancel. So I essentially just rewrite my biggest factorial down until I get to the same number as my denominator. So 9 times 8 times 7, and then the rest right here, that's 6 factorial, right? Okay, so what does this come down to? So the 6 factorials cancel. We're really left with just 9 times 8 times 7, which is 504. Try B on your own, all right? And then check in. Okay, so what we should notice is we have 16 factorial over 11 factorial. So I'm going to keep writing 16 factorial out until I get down to 11, and then I'll just write the rest as 11 factorial. So 16 times 15 times 14 times 13 times 12 times 11 factorial, and I do that because then these guys will cancel. And we're simply just left with what remains, the 16 times 15 times 14 times 13 times 12. And then when we plug that into our calculator, we get our final answer of 524,160. Try C really quickly and check back. Okay, hopefully you got what I did. So we certainly don't want to write 100 factorial out as 100 times 99 times 98 times 97 all the way down. But the good news is all I have to do is write 100 factorial as 100 times 99 factorial. Those guys cancel, and we're left with just 100. Now we're going to get into a permutation formula. Okay, so we'll lead into it. So let's suppose you used to play baseball or Little League, okay, and you're the coach. Let's suppose now you're the coach. There are 13 players on the team. You need to choose a batting order having 9 players in the batting order. Okay, the order makes a difference. The order matters because you can't have the same kid or bat every single time. So, for instance, if bases are loaded and a great hitter is 4th or 5th at bat, his possible home run will drive in 3 additional runs if everybody's on base. So how many batting orders can you perform? So first, I have 9 spots to fill. So I have 9 blanks, okay? The first blank, I have 13 players to choose from. After he bats or she bats, now I only have 12 to choose from for spot number 2. Then 11, then 10, 9, 8, 7, 6, 5. Okay? Remember, I only have 9 spots to fill. So I go ahead, I multiply through, and we get our answer, which is a really big answer of all the different ways you can create a batting order. Okay? So This actually comes from a formula, finding numbers of permutations by writing the computation out. Let's see what this looks like. So we had 3 times 12 times 11 all the way up to 5, right? But if I kept going to use it as 13 factorial, I would need the 4 times 3 times 2 times 1. So that's where I got my 13 factorial. But we didn't want to include that, so I need to divide by 4 factorial as well, okay? All right, so where do we get this formula, or what does that look like? Well, I took 13, that's the number of players we had, and my denominator, I had 13 and I subtracted 9. What did 9 represent? 9 represented the spots we had to fill, okay? And so the permutations of 13 things taken 9 at a time, so 9 positions, and this is our special notation, this 13P9, okay? Is used to replace the phrase, the number of permutations of 13 things taken 9 at a time. So we can write it like this. So this is leading into our formula on the next page. Okay, so the permutation formula that we're going to use, so permutation where order matters, the number of possible permutations of n things taken r at a time, is this formula right here. So this little n, big P, little r, it's equal to n factorial over n minus r factorial, okay? So right now we're just gonna do this formula by hand. In class tomorrow, I'll show you how to use your calculator with it. So the first checkpoint, a corporation has 7 members on its board of directors. In how many ways can it elect a president, vice president, secretary, and treasurer? Okay, so the order matters because there are different responsibilities for each role. I need to pick one person for president and then another person for vice president, so on and so forth. So I have 7 people to choose from. So 7 members, so 7, all right? And there are 4 spots to fill. So 7P4. So using this formula up above, I have 7 factorial over 7 minus 4 factorial. So really that becomes 7 factorial over 3 factorial. So if we needed to write that out, remember 7 factorial is 7 times 6 times 5 times 4 factorial. Oh, sorry, nope, we want times 3 factorial. Okay, and that's going to be over 3 factorial. So I realize over here there is a mistake, so we need to change this. So this is really becomes the 3 factorials cancel, and we're left with 7 times 6 times 5 times 4. And when we multiply that out, we have 840 different ways to elect these positions. Try checkpoint 5 right below with the sitcom television network. See if you can come up with your answer using the permutation formula. Okay, so after reading through, you should realize there are 9 shows that need to fill 5 spots, okay? So we're gonna have 9 factorial over 9 minus 5 factorial, or simply 9 factorial over 4 factorial. Hopefully you realize that this simplifies as 9 times 8 times 7 times 6 times 5, and throwing this onto the calculator, you get 15,120 different ways. Now we're going to get into some permutations where we're rearranging things, and we're going to talk in just a second about what if there's duplicates. So let's suppose that I had these letters, GIA, okay? And the number of permutations, meaning the number of arrangements I could make, is going to be 3 factorial, or simply 6. And let's just show that. So one arrangement I could have is GIA. The other arrangement is I keep G first, but I switch A and I. Then if A is first, I could have I and G next, or if A is first, I can have G and I. And then if I is first, I've got the other 2 arrangements, okay? So there's 6 different ways. So now if I take AVA, how could I arrange these letters? Well, I've got AVA, I could have AAV, or VAA, right? Because A is A, so I can't figure out any other ways to arrange these letters. So there aren't. The answer is no, there are not 6 different permutations. So unlike GIA with 3 distinct letters, meaning they're all different, AVA contains 3 letters of which the two A's are duplicates. So I've got two of the same letter here. So without use of color to distinguish between the two A's, there's only the following three permutations. Okay, so A's we're thinking are just the same. So how do we determine the permutations when there's duplicate items? Okay, so when there's duplicate items, the number of permutations of n items where p items are identical, q items are identical, r items are identical, so on and so forth, are simply this: n factorial over p factorial, q factorial, r factorial, etc. So what does this mean in our AVA situation? Well, let's take a look. So if we have AVA, okay, it contains three letters, so n is 3. There, where two of the letters are identical, so I have two A's, so that would mean P is 2. And the other number is all by itself, it's distinct. So we would have 3 factorial over 2 factorial. And so this would just get us to 3, which makes sense, that's what we came up with, okay? So I want you to try checkpoint 6 with the word osmosis, okay? So in how many ways can the letters of the word osmosis be arranged? Try it on your own and then we'll check back. Okay, so what you should have noticed is we have 7 letters total, so that's our n value. So n is 7. O repeats twice, so we could say P equals 2. And then S repeats 3 times, so Q we could say is 3. So then when we set everything up, we have 7 factorial over 2 factorial times 3 factorial. So I just rewrote it: 7 factorial, 7 times 6 times 5 times 4 times 3 factorial, because I've got a 3 factorial in my denominator. And 2 factorial is 2 times 1. Now when we're simplifying this, the 2 can cancel with the 4 and we're just left with the 2 up top. So that's where I got that guy from, and the 4 went away. So we're just left with 7 times 6 times 5 times 2, or simply 420 different ways that that word can be arranged. If you have questions, make sure to ask in class next time we see each other.